That simple example means the computer will compute WC. The computer will compute WC based on that equations MC WC double dot cos ZC WC dot cos KC WC equal to KC W, and W come from the sensor. So as soon as the computer receive the information from your sensor, then they gotta integrate right away. So the computer will be busier rather than just apply the gain and that's it. So the computer here have to integrate this differential equation to get WC, so that that my U will become minus KC W minus WC. And this overall system, assume your power is not cutting off, then is a mimic to this controller, to this PMP. So this to control these two systems, one is active control, one is passive system, they are equivalent. Of course, we assume that there's no time delay. All right? And also assume that I have a power to be used. And assume that I have actuator. And assume that I have sensors. And again, this passive system, the disadvantage of passive system is KC and ZC cannot be changed arbitrarily. You may not find the KC you need on the market, right? The spring, can you find all the spring you need to have? No. On the market, maybe some special spring and with some special stiffness. That's all. And you got to live with it. The same, the ZC is the same thing. In the market, you may not get the ZC you want. But here, in theory, that you can have any positive values of MC, ZC, and KC. I say positive values. Right? So you have all kind of fitting for this. So this is the key advantages of the active control system. Now we move in this class. Now we gradually move from passive system to the active system. So this is the mimic. I say this is mimic this controller. The same thing. However, if you can solve your problem by a passive way, then you'd rather use the passive system because you don't need power. Right? But the passive system, another disadvantage is one-on-one, the passive, this ball is huge. Any questions? This is I call mechanical analogy. So for any control system, you can do it passively or you can do it actively. No problem. All right. But this one here, again, we use only the measurement of displacement. And that measurement displacement in combination with the controller dynamics will provide you the damping for the system. So if you have a displacement only, you need to either differentiate that or you need to add dynamics to your system. you need to add also virtual displacement. Okay? Understand now? So that's the importance of dynamics. Alright? And this one now, let us look at the accelerations. What is the differences between the displacement and accelerations? The accelerations means the w double dot. Alright? And these accelerometers, if you look at these accelerometers, is just a TMD. True. All the accelerometers designed like this one, well, unless there are something new, some new one is a little bit different. There's a piezo materials. But the conventional accelerometers is just a TMD. So TMD is really used in a lot of different things. Even the device, the accelerometer device is nothing but a TMD. Of course, this M is small, K is small, CV is small, so that they will affect your system when attached to it. Small. Okay, so this is the measure ranges from 0 to half by 100 G, and this is just frequencies from 2 to 9,000 Hertz. For low frequencies, the accelerometer is not a good idea. If you want to measure frequencies like 0.1 Hertz, 0.01 Hertz, this accelerometer may be huge. For small accelerometers, you can measure only the somewhat high frequencies. Right? For more than 2 Hertz, that's only very accurate. Okay? All right. Let us come again. Look at this screen again. You know, very simple screen. Now I'm talking about the accelerations. But now here, my displacement WC is a relative. It's not absolute in here. Be careful. Now this is a relative displacement. That's a WC minus W. So here, if I use absolute, then my equation of motion will be mw dot plus kw equal to u equal to zc wc dot minus w dot plus kc wc minus w. But if you add relative, wc dot prime plus kc wc prime, that's a relative displacement. In other words, that's just you stand on the mass here and look at the motion of the MC. Alright? So in accelerations, we commonly use the relative because you'll see that it will make our virtual system much simpler. Alright? And if we use absolute, that's the equation MC WC double dot equal to MC W double dot plus WC double dot, right? Prime. That becomes absolute. Then equal to minus U, that equal to minus, that's a minus ZC WC dot prime minus KC WC prime. Why we want to do this? Because we want to have a form exactly the same as the system form. So here, if you look at this, MC WC double dot prime plus ZC WC dot prime plus KC WC prime equal to minus MC W double dot. That's almost identical to the displacement feedback, except here we become accelerations. But we are using prime because if we use prime, my formulation is almost identical to my displacement equation. That's the only problem. But if you want to insist to use absolute, it's fine too. I'm not saying that it's not good. You could do that too. But to make your equation prettier, then this is better. And that's all. Any questions? This is just a simple equation of motions that easy to derive, right? There's nothing that you can know. Everybody knows it. Any problem? No? Okay. So my dynamics, one degree of freedom again, is like that. mw plus kw equal to u equal to minus mcwc double dot. Alright? Equal to m minus m parenthesis wc double dot plus wc double dot prime. Okay, look at this prime. And the prime will be calculated by computer by this, the following formulation of the mc wc double dot prime plus zeta c wc dot prime plus kc wc prime equal to uc equal to minus mc wc double dot. So as soon as we receive information from our accelerometers, w double dot, we can integrate these equations to get my wc double dot prime. Okay? Because I have to use that here, right, for my feedback. Any questions? But this seems to be easier because MC double dot prime, you don't have to really integrate, but you do have to integrate to get the WC prime and WC dot prime, and then you just move these two terms to the right hand side, and that's all you need to do. However, now, your accelerometers, depending on your accelerometer may measure the absolute accelerations or may measure the relative accelerations. So if your accelerometer measures the absolute, then the equation will be a little bit different. Okay? All right. The general system, the same thing. The general system, the same thing. Exact the same as the dispersion feedback I'm using here. If you check the dispersion feedback, then you can see they are identical equations. They are identical equations. There's nothing different.